through the rest of the week, and greetings to everybody online. I know we're going to watch a lot of these on video later on. We're really glad y'all have joined us today. So our second to last speaker is Dr. Jennifer Jordan, who has recently joined us from the Munitions Directorate at AFRL coming out of Eglin Air Force Base. She's a brand new addition to our group, so this will be her first spring review talk. She's got a new portfolio within our department called Dynamic Materials and Interactions, and she's been very active in a number of professional societies. And if I could read my I'm getting older. She's actually been a recipient of the Air Force Science, Technology, Engineering, and Math Award in Research Management, and she's an active member with Society of Experimental Mechanics. That's what I want to get to, and APS. So with that, Dr. Jordan, we'll turn it over to you.
Thank you. All right. Thank you, John, for the kind introduction. Thank you, all of you here and out in TV land who have stuck with us through the week. And John didn't use it, so I'm going to use my favorite word. I'm going to give the penultimate talk. I just have to say they saved the best for last. So as John mentioned, I'm a new program officer here at AFOSR, and I have a portfolio in dynamic materials and interactions. And throughout this talk, you're going to see what that means, but I want to start with a motivation. Why are we interested in these kinds of in this kind of research? And so really what we're really trying to do is enable sixth-generation aircraft because they demand munitions innovation for a variety of reasons. The first is the internal carriage. This is going to constrict us in size, and so we're going to need things that have high energy density, that are multifunctional, and also that maintain in sensitivity. They're safe to handle. Additionally, there's the Air Force mission for survivable penetrators. So we're really interested in mechanically induced damage in energetic materials, as well as survivable energetics. Traditionally, energetic materials development lags munitions development by many years, and so we're really trying to increase the development time. And this leads us to needing things like energetic materials by design and predictive multi-scale modeling and simulation. And then finally, due to the delivery environment, either the internal carriage or for long-range strike kind of applications, we're looking at high-temperature delivery environments, which we haven't really considered before for energetic materials. And this leads us to need thermally stable energetic materials. And so this portfolio, Dynamic Materials and Interactions, was put together to address some of these concerns. The portfolio is concerned with the fundamental basic research into the dynamic chemistry and physics of complex materials, particularly energetic materials. And so what do I mean when I refer to these kinds of materials? They're across really a spectrum of materials, starting with traditional explosives, where we're looking at organic explosive crystals that may have a fuel or oxidizer component in a polymer binder. These are going to look very similar to some of the solid propellants that Mittat talked about earlier. We're also looking at reactive materials and structural energetics. Typically, these are metal-metal oxide type reactions. They typically don't contain an organic phase. And then also we're looking at energetic materials that don't fall into these two traditional bins. Things maybe like a core shell nanoparticle where you have fuel and oxidizer in the same material. If you look at the microstructures of some of these materials, you can see that underlying them is a need to understand composites and polymers. And when I use the term composites, I mean particulate composites rather than the traditional fiber-based structural composites that you might consider in other air applications. So I want to take the next part of the talk and talk about 3 research challenges that I've identified based on this motivation for this portfolio. And then I'm going to turn these research challenges into the research areas that we're considering in the portfolio. So the first challenge is energetic materials science. Dr. Ali gave a very good discussion earlier about why we needed predictive materials science. To this formulation of these materials. Typically, we have a linear formulation process where we consider ingredients in some sort of processing technique to create a given microstructure or product. And then we test these materials for performance as well as survivability, things like mechanical, thermal, and insensitive munitions. Now what's interesting about energetic materials is that in order to get to the scales where you can do tests that are relevant to the kind of systems that you're interested in, you've undergone a huge scale-up process. We don't start making energetic materials at the hundreds of pounds scale where you can do some nice sized relevant tests. We start at tens of grams, because you don't want to blow your fingers off. So you've already invested, by the time that you get to where you can actually do relevant tests, you've already invested a huge amount of resources into these energetic materials. And so what we really want to be able to do is couple modeling and simulation with this experimentation so that we can transform a formulation from empirical to predictive, which is exactly the kind of arguments that Dr. Ali gave earlier this week for metals and some other materials. The second challenge that I want to talk about is shock propagation in heterogeneous materials. By heterogeneous materials, I mean, again, those particulate composites where you have some sort of particulate phase. Typically, it's harder than the matrix phase. And two example materials that are considered in the portfolio are concrete and polymer bonded explosives. We've already talked quite a bit about the energetic materials part of the portfolio, but you'd be surprised about the mechanical similarities between concrete and PBXs. So what we really want to be able to do is understand how a shock wave propagates through these heterogeneous materials and how it's affected by the particulate matrix interactions where these materials have considerably different impedances defined by the sound speed times the density. So in a homogeneous material, for example, a pure metal, you might see a rise time in pressure as being extremely sharp. But in these heterogeneous materials, you start to see that this shockwave rise time becomes dispersed and is dependent on the material mesostructure. So what we're really trying to understand for this challenge is, can the shockwave be controlled by manipulating the microstructure? And then the final challenge that I want to address in the portfolio concerns performance of energetic materials versus their sensitivity. So there are two observations that are relevant for this challenge. One has to do with the performance of traditional carbon, hydrogen, nitrogen, oxygen explosives. This performance, which I've indicated here through a metric of detonation velocity, has really plateaued. This is year of discovery down here. But you can see that the cost has risen dramatically to achieve those small increases in performance. By traditional CHNO explosives, I mean these kinds of complex molecules down here that you may have heard of even in the popular press and on TV. The other concern is that as you increase the performance, again here this is the detonation velocity, and you measure a indicator of the sensitivity, in this case the impact sensitivity, you can see that as the detonation velocity increases, the impact sensitivity decreases. You would think this would be good, except that a low impact sensitivity means that material is much less safe to handle. So you've got this a little bit of a paradox, whereas the sensitivity increases as the performance decreases, so you're getting a safety risk. Sensitivity increase, depends on how you would use the word sensitivity. So now I want to talk a little bit about my investment strategy and then lead into the actual research that we're doing in those areas. When I was considering the portfolio, I started thinking about scales. I'm a material scientist. I like to work in the microstructure scale, but I started thinking about the different scales that we're concerned of with the energetic materials. And so you have things like developing new energetic crystals and molecular dynamics, the kinds of scales that Dr. Berman discussed earlier today, all the way up to scales where you're actually doing explosive formulation and scale up. And I took those three challenges and I started thinking about what scale is going to be the most relevant to understand what is going on for these materials. And when I did that, I saw that really what becomes very relevant to my portfolio is the mesoscale, where the mesoscale here is defined as the microstructure of the material, basically what you can see in a given micrograph. Additionally, you can see that there are a wide variety of organizations that are working on energetic materials across the DoD. And so one of the things that I wanted to do was start getting that community together. They had already started organizing with things like a joint review last year and try to draft some sort of energetic materials basic research plan where the program managers across the basic research organization in the DoD who are concerned with energetic materials are all kind of looking at the way forward in a similar way. And additionally, enabling the long-term availability of an expert knowledge base with a consistent investment in this type of research. Energetic materials suffer from the aging of the workforce, where a lot of the expertise is walking out the door very rapidly. So if you take those 3 research challenges and instead think of them as research areas, what can we do to understand and invest in those areas? That's what I'm going to cover for the remainder of my talk. I'm going to start with transforming energetic materials from empirical to predictive, where again, we're looking at coupling modeling and simulation with experimentation to do predictive material science for energetic materials. This is really driven by the vision for a virtual design studio for energetics, which I'm going to discuss in detail in the next slides. And then I was lucky enough to have 2 FY15 basic research initiatives starting in this area. So this is really the research area in my portfolio that is up and coming. And what we're concerned with here is addressing the traditional material science pyramid of performance, processing, structure, and properties, particularly for energetic materials, where performance looks like things like blast and fragmentation. So this vision of a virtual design studio for energetics, what are we really trying to do? We're looking at developing a predictive computational tool for explosive and reactive materials formulation on your desktop. And I use that term desktop to mean that it's user-friendly for the formulator. Formulators typically are experts in chemistry, they're experts in material processing, they're not experts in computation. So it needs to be a user-friendly tool. Additionally, we want it to be informed by the best science. And this is where the basic research investment in this kind of tool comes into play, where we're looking at the fundamental physics and chemistry of the energetic materials and the response to mechanical, thermal, and other loading. At the 6.2 level, this is a partnership with the Munitions Directorate, where they're actually looking at development of the software and validating it against experiments on real complex explosive formulations, things that we wouldn't consider in academia. So what does this mean for basic research? We're looking at new energetic materials. What kind of characterization do we need to do in order to understand new energetic materials and describe them computationally? Looking at the processing, structure, property relationships and the mechanical response of those materials. And then ultimately the initiation and reaction propagation through the materials so that we can predict both survivability and performance. So I want to start with describing one of the BRI topics, which is in situ dynamic mesoscale measurements of reacting energetic materials, which very much aligns with this vision of a virtual design studio. Here, what we're trying to do is actually do real-time, which in this case is very fast, measurements of stress concentrations in these energetic materials. These stress concentrations can be develop into hotspots, which is where energetic materials tend to initiate. So we really want to understand how hotspots form in energetic materials so that we can understand and control initiation by controlling the microstructure. And so in order to do this, we need to characterize 3 different aspects of the energetic material. We need to have microstructural characterization here where property distributions are key. We can't just report an average particle size, but actually have to understand what the particle size distribution is in the material and how to describe it. Dr. Ali gave very good reasons why we needed to be able to very accurately describe the microstructure. We want to do micromechanical characterization, where we're actually looking at how stress concentrations form at the microstructural level. In this case, this is a digital image correlation on a microstructure where we're actually seeing strain concentrations in the material. And then finally, we want to be able to do microfunctional characterization, where we're actually looking at temperature in the material at the microstructural scale. If we could combine all 3 of these together at very fast time regimes, then we would really be able to understand initiation in energetic materials and actually design materials. And so that's the purpose of this FY15 basic research initiative. I do have some current research within my portfolio, that's addressing each of these topics, and so I'm going to talk about that. The first one is looking at damage and sensitivity in energetic materials. This is primarily experiments at a continuum scale, where they're taking an as-processed block of explosive, They're damaging it by applying a shock wave to it, recovering the material, and then looking at the microstructure again to see if they can see any differences between the as processed and what we would call a damaged microstructure. And then they're taking these materials, both the as processed material and the damaged material, and they're determining the run to detonation, which is a measure of sensitivity in the material. How long does it take the shock wave to turn into a detonation wave in the energetic material? And they've observed a couple of things, but there's still a lot of uncertainty in these measurements because we're considering what is really a mesoscale phenomenon at a continuum scale. They have seen an increase in sensitivity with damage, particularly at low pressures. At high pressures, you're really overdriving the explosive. It doesn't matter what kind of damage is seen, it's going to go. But at low pressures, you're going to start to see some of those microstructural effects. This low pressures is important because this is where you have issues with things like insensitive munitions and survivability. Additionally, they did see that changing the binder did result in a decrease in sensitivity. It gives an indication that the role of the binder, even though it's the inert component, can be quite important in the energetic material. So we really need to understand those polymers. So that was the microstructural characterization. Looking at functional characterization, Dr. Dana DeLotte at the University of Illinois has developed an IR microscope to see hotspots in real time. In this case, real time is much slower still than the timescales that we're thinking of for the Basic Research Initiative, but really he's able to start to understand how interfaces are playing a role in initiation of energetic materials. In this case, he took two sugar crystals. One was uncoated and one was coated with a polymer. He heated them up using a ultrasonic loading technique, and you can see that the coated crystal showed a much higher temperature increase, actually, than the uncoated, which showed almost no temperature increase, indicating that the viscosity at that polymer crystal interface is controlling at least the acoustic hotspot generation. And so these kind of measurements, if we could speed them up, is the kind of thing that we're looking at for the microfunctional characterization. And then finally, looking at micromechanical characterization. As I mentioned, this is a new portfolio, and I was able to borrow some grants from other program managers. And so I saw some potential in this particular grant, which is a young investigator grant with Dr. Gary Seidel at Virginia Tech, for trying to understand damage in energetic materials. What he's doing actually right now is using carbon nanotubes as in situ damage monitors for aerospace structural applications, particularly for structural health monitoring. But I could see that this may be relevant to energetic materials. We could actually use the same in situ techniques to do damage characterization in energetic materials. So over the next couple of years, he'll still be working on on the aerospace structural aspects of the grant, but hopefully slowly steering him over to looking at energetic materials through the course of the portfolio. So we revisit this BRI topic one more time. What we're really trying to do is develop predictive models for the energetic material initiation. Right now, the state of the art is that there are very good mesoscale simulations predicting the initiation of energetic materials. And what they do is they hop out of this, they determine the temperature distribution. They say some of these hotspots of a particular temperature and size, and they plot them, and they compare them to an empirical initiation model. And if it goes above the empirical initiation model, they say the material has initiated. What we really wanted, so these simulations, which are state of the art for the mesoscale, are still looking at a go, no-go kind of criteria. Ultimately, what we want to be able to do is actually have mesoscale simulations that are predicting hotspot propagation based on including localized chemistry, and that are validated with experiments measuring real-time hotspot size and temperature. I use this as an example. This is work by Dr. Wayne Chen, not in my portfolio, but where he's actually looking at the impact of 2 sand grains in a split Hopkinson pressure bar, so stream rates of about 10 to the 3 per second, using the argon beamline, where he's actually seeing the fracture of 2 sand grains, or the fracture of the sand grains. This is the kind of scales that we need to get at for the kinds of experiments that I'm talking about in this BRI. And these kind of preliminary results on inert materials give me a lot of hope for what we'll be able to do with the energetic materials. So I'm going to switch gears a little bit now and talk about the second basic research initiative within this research area. And you've already seen this slide today because Dr. Schmischer put it up in his introduction. This BRI came about when we were sitting around in the department and learning about the work that that we were all doing, and as I was coming in new, and I realized we were starting to use some of the same words or describing phenomenon that sounded very similar to me. And so I wanted to know if there was similarity went beyond just superficial. So we started thinking about these different kinds of applications, which are some of the applications that our portfolios address, and the materials that are concerned with them, namely ablative materials, reactive materials, propellants, and explosives. And so we were thinking about reactions in these kinds of materials. And so the first thing that I did, being a good material scientist, is I pulled the microstructures, because I was curious, do these materials look kind of alike? Is there something that, that we can say qualitatively about them? And it turns out they're not hideously far off. So if you look at the microstructures of these materials, what you'll see is you have composite materials, and you typically have a hard phase embedded in a soft phase. Okay, so qualitatively these materials look kind of alike, and they are reacting if you consider the ablation of these hypersonic materials a reaction. So we started to think a little more and realized that basically we were considering non-equilibrium condensed phase reactions. And these condensed phase reactions, which are extremely difficult to model, are really key to understanding what's happening in these materials during a steady state reaction. And so what this BRI is really concerned with is addressing this thin reacting layer that's on the surface of the material. It's in contact with high energy gases, as well as unreacted material that maybe doesn't even know the reaction is coming. And so to look at this a little bit more qualitatively, we were wondering if we're even in the same pressure and reaction rate regimes for these materials. And so we had some simulations as well as some experimental data, and we're looking at these materials, and you can see that actually the pressures aren't hideously far off. You're in the range of 1 to 10 MPa, and also in the range of 1 to 10 centimeters per second for a reaction rate. So this gave us some comfort that the energy and mass transport across these interfaces is occurring at comparable pressures and reaction rates, and that maybe these two communities, by working together, can really start to delve into these condensed phase reactions. And so what we're really trying to address within the BRI is how to determine the rate-dependent chemical, physical, and fluid mechanics processes that are occurring in this, what we call the interface region, this thin reacting layer on the surface of the material. And there's some work that is currently funded across all of our portfolios that gives us some indication that we may be successful by combining these communities. This is work in Dr. Mitat Birkin's portfolio, which I think he showed a little bit earlier, where they're actually looking at an AP aluminum propellant and trying to understand the mass flow in that thin reacting region. And so that's the start of the kinds of simulations that we need to be able to do to understand these materials. I think John will talk about his MURI, where he's concerned with the high energy gas above the reacting surface up to the first atomic layer. So we'll be able to leverage this research as well as research within the energetic materials community, so that we don't have to concern ourselves with the gas phase chemistry. We can concern ourselves with the condensed phase chemistry. And then experimentally, Dr. Dana DeLotte had an interesting idea, which was that can we scale the experiments so that although the molecules aren't in an actual detonation, they think they are. And then we've scaled them to such a way that we can actually use the kind of probes and techniques that we have to really understand what's going on in these materials. And then finally, we'd like to be able to visualize that reacting interface zone. This is actually AP particles flying off during a reaction. I think the videos in Mitat's presentation earlier today give a very good picture of the kind of visualization that we need to be able to do to understand this reacting zone. Okay. So I'm going to switch to the second research area. I mentioned that the first one is the up and coming in my portfolio. The second area is kind of the stable area, which is kind of a funny thing to say for a portfolio that's only been around for 9 months. But this is the one where there was an investment in AFOSR that moved into my portfolio. Dr. Lee referenced it, I can't remember if it was yesterday or the day before. So we're going to talk about controlling shock propagation in heterogeneous materials. So what we're really trying to do is understand how shock waves propagate in heterogeneous materials and ultimately engineer microstructures to mitigate blast loading. We're lucky enough to have a center of excellence in this research area. And one of the things I want to highlight about the Center of Excellence is the educational exchange with the AFRL. A Center of Excellence is funded half by AFOSR and half by a TD. In this case, that tech directorate is the munitions directorate. And I'm going to give an example on the next slide about how people and technology are changing back and forth between the TD and academia. So this is work in Dr. Ravi Chandran's lab at Caltech, where he's looking at trying to understand how the shock wave is mitigated by particulate composites by changing the microstructure of the composite, in this case the volume fraction and the particle size. And so what they're doing is they're impacting these materials that have glass, I think they're glass beads in a PMMA matrix with varying particle sizes and volume fractions, and they're measuring the free surface velocity off of these materials. The free surface velocity is an indicator of the pressure or the shock velocity in the material. So here you can see some of the results where they had 3 different particle sizes, and then as they went to the largest particle size, they saw a dramatic increase in the shock wave rise time over the other materials. So they're really starting to understand how that microstructure can control the shock wave rise time. But I think what is even most interesting about this research is that these experiments were actually conducted using the HP3 facility, high pressure particulate physics, at Eglin Air Force Base and the Munitions Directorate by graduate student Mike Rawls over the summer through an exchange through the Center of Excellence. There, he learned how to use something called particle image velocimetry, which is a technique for measuring this free surface velocity that's really up and coming in shock waves. And he was able to take that and transition it back to Caltech, where their lab had been just a smidgen dormant over a couple years, and actually increase the capability of the lab. And at the same time, form real good scientific connections with RW. So I think this is really one of the biggest benefits of the Center of Excellence construct is this exchange of ideas, technology, and people between the labs and academia. One of the ways that they're using this idea of being able to mitigate the blast wave in the composite materials through the Center of Excellence is this idea of what they call a meta-concrete. And in this material, what they do is they take a heavy core, in this case lead, and they surround it with a soft polymer coating, and they embed that in a traditional concrete mortar. And here you can see the experimentally, but what they're looking at is as they propagate a shock through this material, they're actually capturing the mechanical energy in the vibrating lead cores, and it's mitigating the shock wave as it propagates through the material. So they've been able to determine this computationally, and the next step is to actually build these materials, the aggregates and the concrete, and ultimately test them to see if their predictions are true. One other area where we're very interested in understanding shock propagation is through granular materials. And in this research, which is a joint project between Georgia Tech, Harvard, and Marquette University, they're looking at very well characterized sand grains and doing shock experiments on them, very similar to what I described for the particulate composites. And they're looking again at, this is a stress, I guess, in this case, versus time, and trying to understanding what comes out of the energy out of this sand material, but actually trying to understand what's going on during the experiment using mesoscale simulations, so they can understand things like interparticle friction, particle fracture, and phase changes, and how those are affecting the experimental results that they're seeing. So finally, the last research area, and this one's going to be quite brief because it's only one slide, is performance versus sensitivity. So as I mentioned, the first one is up and coming, the second one is established, and the third area is the area that I want to look at in the future. So here, we're really trying to understand how sensitivity is related to performance in energetic materials, looking at the molecule and the crystal response to shock loading. Here's the formation of shear bands in an energetic molecule. This is using molecular dynamics kind of simulations. But ultimately really trying to get at what makes an insensitive explosive insensitive, and then also using what we learn about materials, existing materials, to formulate new energetic materials. One of the areas that I would collaborating on is Army Muri, where they're actually looking at co-crystals of energetic materials. They crystallize 2 different molecules in the same crystal, and this can give you some benefits in both sensitivity and performance. And so as I said, this is the area of future emphasis in the portfolio. So I want to finish up by just reiterating the 3 research areas that I'm looking at going forward. We're looking at transforming energetic materials from empirical to predictive. We have 2 research initiatives coming about in this area to really to grow it, and we're driven by this vision of a virtual design studio for energetics. We want to be able to control shock propagation in heterogeneous materials, which is going to give us benefits in both blast mitigation, but also ultimately will have payoff in energetic materials. And again, we have the Center of Excellence, which is providing some excellent benefit both to the lab and to the academic performers. And then finally, in the future, starting to really look at performance and sensitivity in energetic materials, and also through that new energetic material synthesis. Thank you.
Any questions or comments for Dr. Jordan? Right, nice talk. We're really pleased to have you part of the team and look forward to a couple of other great presentations in the future. Let's see how this is going to work. So hold this for a minute.
Yep. Is somebody introducing you?
No, I'm going to.
You're going to introduce
Actually,
you?
I got an idea here. See if this works. So it's been a long week. I know that everybody is tired. This seems to work at Virginia Tech football games. So I thought I'd give myself some walk-up music. Faster, come on. So anyhow, it turns out when Virginia Tech does this for a football game, they've got their guys all kind of queued up, so the building part of that, the student section goes wild. We'll maybe switch to the lavalier mic here, so we'll put this down.